Yeah, it's been a sec. I wanted to talk about this for a long time, and then I just didn't do it because I just didn't feel like it, you know? Let's get into it. Okay, so I've read this chapter a couple of times. I was hopeful I could glean something interesting to talk about, at least in the text. There's just not a lot here that's particularly interesting. Yes, I could read all the macros, assert not equals, assert equals, should panic as an attribute, the way that the modules are set up. You can just read that, you know? It doesn't really have a lot that's interesting. I think that the best way to kind of jump into this is to go into the code. There's one thing I guess I want to talk about, the difference between unit tests and integration tests, and I'll try to tie a nice little bow on it when we get to the code. The long and the short of it is that integration tests test the public API of whatever you're trying to actually test, and unit tests are as small as you can get. Essentially, for every function, you're going to be trying to change all the inputs and make sure that you get the correct outputs. We don't do a lot of integration tests, at least with the stuff that we've written thus far, because let's be honest, most of the time your public interface is something that requires a decent lib.rs, and we haven't made one of those yet. Though I do think there is something interesting, at least on the unit test anatomy, that I'd want to bring up on top of this. So set up any data, run the code, assert the results are what you expect. There's another secret hidden one here, which is like cleaning up. And I figured out a way to do that using the drop traits, which are kind of the resource acquisition is initialization. So when you get whatever resource you want from the computer, your memory, you initialize it, right? You kind of have to do that. And then C++ was like, we're going to make that a kind of standardized thing. So then you have like getters and setters, you're initializing things. It's like kind of an object-oriented way of approaching it. I don't necessarily like that, but there's a way that we can use that to induce side effects, sorry, functional programmers, to make sure that our teardown happens, even in the case where we're going to like panic inside the function. So think about like wrapping a function with some stuff. It has to happen even if we panic before the function's complete. I've talked too much, frankly, and I'm just looking at what I have here. I don't have anything to talk about other than stuff on the computer. So let's go to that. Cool. So I'm going to show that we are in the same group, or at least a directory that represents the same group that I showed you on GitLab. I initially had set up one repository, and then in the CI/CD I had a grab all of the directories with chapter in it, do cargo test on that. But I actually don't like this for a couple reasons. Firstly is the last example, I think maybe the last example, chapter 10, we're doing some file tests. We ended up writing a bunch of here's how to handle stuff, question mark operator, unwrap, expect, all that. And when you do that, you have issues with the file system that may cause problems if you have the same file that's expected to be there for two tests, because it defaults to multi-threading and you will make race conditions. So if I look at that, let's go to, I think chapter 10. No, chapter 9. So chapter 9, we wrote a bunch of functions that read from files and then take the contents of the file and returns it as a string. And in this case, we primarily only seeing the standard OK match in both of these matches. The errors are hard to produce because, well, I'd have to like change mod the directories that they're in, and that would be annoying. You can see how that could cause problems with other tests executing. If I look down here where I'm actually testing it, I have a couple things. I usually call the connecting the way I expect it to, not really going into any error cases, my happy path. So I put that at the end of whatever the test function is. And you can see we have another one where it's expecting to panic, and we're getting to use the expected there with the exact string. So in this case, reading the file contents panicked, we're trying to hit this particular case. There is a way for us to actually view what lines have code coverage. It appears that that's LLM tomfoolery, And while I can say that I've done it, I don't really want to jump into that because that's much further in the book. Largely, we're just going to be writing tests to a level that allows us to be confident in our code. I tend to think of tests as, well, I'm not very experienced, but I will say with whatever low wisdom stat that I have, tests primarily exist to allow you to know where to start debugging code. When things go wrong, that's when you know, okay, I've tested these things pretty thoroughly, so it's probably not there. Then I'll just set theory. Everything that I haven't tested is probably where the bugs are, or at least the bugs that I'm talking about being really complicated and not just read the stack trace level bugs. Anyway, when we look here, we can see we have like config.yaml in this one, and then in this other function down here, we're using this file does not exist.txt, and then we have hello.txt in a couple of these other ones. The rub with all of these is that so long as I have multiple functions or potentially multiple tests that are calling the same function, these files may or may not exist at the time that we're actually testing them. The way that we test that is with this try exists, which exists off of, in this case, path, but inside of the standard file system. What it eventually calls to in standard file system is our stat call and then get file information by handle, linked to, I guess, the documentation where it says that. So there's like a time difference between when we call this, when we write to it, when we check its contents, and then lastly, when we like clean it up. Oh yeah, I need to talk about cleaning up. Anyway, the point is, with this particular kind of a test, we actually have to invoke our tests differently, because in the case where we're actually trying to run everything and all those tests could be running in parallel, it will break. Let me grab this cargo test example line here, and we will try running it without the threads on it, just to prove my point. So we get failures, right? And it's saying it's failing. Well, let's look at the verbose. Yeah, hey, that was quick. Okay, so it's actually saying like, hey, I can't remove this file. It didn't work, right? Like something happened. And that's because, well, we're running 9 tests. I'm not sure how threaded that is by default. Is it in the book? Okay, it doesn't say how many are there by default, but that's why when I originally had my example, we had test threads 1, test threads 1. So when I run it with 1 test thread, it means that they have to run sequentially. And because of that, each test is able to write the files it's expecting, delete the files it's expecting, et cetera, et cetera. How does that work? Well, let's jump into that. I might want to do a slight tangent. Sorry, the reason for the apprehension there is I also want to talk about chapter 10, but now we're in chapter 9 and now there's no order. All right, our happy path here. So we have a couple things that maybe are worth talking about. Same stuff that's in the chapter, but different context. So we can see our return type is result. I don't know if there's a like generic standardized result that would be able to accept whatever is inside of a result for everything else, right? Like I'm using standard IO because that's what we're actually testing with in our original function. And that means that when I pass OK at the end, it will be fine. And I don't have to have any more imports, but like, I don't know if that's right, so maybe that doesn't need to be that. If I just change it to result, I seem to have problems. Yeah, it's expecting 2 arguments, and so it's like, okay, but then when this runs as expected, it's like, well, I can't actually handle that with the question mark operator there, so it just kind of made sense for me to use what already existed in the function that I'm testing. Obviously. Okay, anyway, the anatomy of this, that's the cool part. So here we have a setup. I'll explain how that works in a second. And then we have our regular stuff, right? Like we make some sort of state in order for us to pass in the input to the thing we're testing. In this case, I'm simply just saying if this path for config.yaml does not exist, we're good to go. Otherwise, we panic. So somewhere else the cleanup didn't happen. And these kind of asserts here are at least useful in knowing that, okay, this issue was a threading issue. It was a race condition as to why it wasn't working earlier. Then we can say, cool, let's make sure that config.yaml exists and that it has, test and all this stuff in here. We can do that. We can write it with the helper function that we learned about a while ago. And then we can say, great, let's actually read from that and then make sure that the output of that string is equal to what we expect. So there are 3 pieces. So the fourth piece is cleaning up, right? We already ran into this issue with race conditions. Let's jump up to this mysterious setup thing. So we have a struct setup. It is not an interesting struct, but what we can do is we can have a method drop exist for setup, and this drop is special. It gets invoked whenever we actually have to, when the lifetime of the struct dies. And so by setting up that setup at the beginning of a test here, we don't even care what it is. We just care that when this function's done, regardless of however this function is done, a panic, a failure, whatever, that we will do whatever is in the lifetime killing part of setup. So this drop for setup is actually doing some fun stuff. Basically, I'm doing the same thing, the same test. Hey, if this exists, then make sure it doesn't exist, like remove the file. And that's not super interesting. It's 3 different ifs. There's a much cleaner way to write it, but I'm not really interested in making a cleaner way to write it right now. I'm interested in testing things. So wherever I have this set up, wherever I actually instantiate this struct, we guarantee that at the end of its lifetime, i.e. the end of this function, that we are going to delete whatever config.yaml was that we were testing, because, well, 1, we expect it to not be there at the beginning of the test, but 2, we actually are writing to it. If we have 2 different things writing to things, it's a mess. So right, this is our quick way of ensuring the state before each test is actually correct, which is part of the setup, but it's also part of the cleanup. That was not addressed as much as I would have liked to hear in the testing. It's the kind of stuff that you see when you're actually trying to test some code that maybe wasn't obvious from the chapter. So cool little example. Unfortunately, the rest of these tests are not very interesting. So, when we have a panic, we don't really care about what happens with whatever we've created. It's expected to panic. And so boilerplate does this panic with the error we expect. And that's kind of it for this one. I have one other fun one. So this test read from file question syntax throws. Oh, okay, this one is interesting. I had another one that was an example above, but we normally, I'll say, like to use the question mark instead of this unwrap, but we can't do that because where would this raise to? It needs to be inside of this function, right? And so we could change the output and try to make it happy, but what we'll see is we can't actually have this result on a should panic, right? It's saying should panic must return our unit struct, unit tuple, and that's not what we're looking to do here. So we just simply fix that by taking all of our stuff and unwrapping it, and it works fine. And yeah, so I guess I could have just said that sentence, but examples. Rad, so that's that example. I'm going to do a quick walkthrough on what I did with chapter 10. I think this one, okay, so this has different structs we put in different modules to kind of have them be in different structs, but nothing super crazy. A lot of our lifetimes, generics, that kind of stuff. What I really did to break out these tests is more of like copied all the things that were happening in main as though they were kind of integration tests, because what we were doing was we were essentially doing a test with main. We were making sure that the output was what we expected, at least in the chapter. Oh yeah, I didn't mention this as well. It's in the book, but we actually want to use the asterisk use, that import there, because it allows us to say everything from the module above, i.e. the root of the crate, needs to be accessible so that we can test it. So that's why we can call things like largest and distance from origin and all that stuff without actually having to do like a weird pathing thing. None of this is particularly interesting, at least outside of what's already in the context of the book. There is this dereference guy here. Our largest is actually returning a reference, and that means in order for us to make sure it's equal to something, we actually have to dereference it. Where we were using it in the code, we could simply just print it out because the string or display trait for it is just going to make sure that that ends up as the string we're expecting it to be in standard out. We don't have that luxury when testing, so we have to make sure that we have a dereference guy. That's pretty much it for 10. Let's keep going. For chapter 7 and 8, we actually have what would be a good example of integration tests and unit tests. Let's go over the unit tests first. So we actually have our payment gateway and storefront, I believe, that had some stuff in them. Yeah, so here's our test module. Again, nothing super crazy, at least in terms of what we read in the chapter versus what I had to do to write tests for this. You can see there is some logic in me having to set aside, here's the expected path for when everything's working as expected, and then there's the path when something doesn't work as expected. So largely, that's just me changing whatever this input is. We can see the value here is the main difference between this happy path and declined, and it has to be associated with the balance. One thing that's maybe a little different is I try to come up with the edge cases. I don't have my hands to wave. We obviously know if the person has $1 million and the item costs $100, yes, that's worth testing. But what happens if they have $1 million and the item costs $1 million? We now know that there's some amount of tax that's associated with it, and the tax would make it more expensive than what the label is on the store. At least if you're buying stuff in America, the tax is not included in the price. It's an edge case, right? Like that tax there is something that it's easy to forget about and can cause problems. So it's easier to work with like very large numbers and like things just to the scope of where something might roll over. And those edges, those are what we test for. Wow. All right. Yeah, knowledge bias. All right. Okay. So I have a comment here. I guess we haven't covered the not logical operator. So not will apply to everything after this. And since RSP is a Boolean, we can say not whatever this output is. So RSP I'm expecting to be true, and I want to assert that it's false. So I put the not there. I was using that in the chapter 9 example in the if statements and the asserts for the files existing and being removed. Sorry that I didn't make that clear. That's not in the book for some reason. I think this is obvious if you worked in other languages, but maybe wasn't obvious here. Anyway, that's pretty much it for this file. Let's look at the storefront. So this storefront actually has this purchase, and it's public facing. And well, if we look at what our main says, you'll see that our main actually is using purchase as like its primary example. If we're taking this to the whether this is a unit test or integration test, it's closer to me towards an integration test. It's actually how we would interface with the public API, and well, purchase is public. But I wrote it as a unit test because it seems to make more sense to me when I can just set it up directly right close to it and control the inputs and the outputs. So you'll see that I have this idea of decoupling something. The balance here is going to change, and the inventory quantity is going to change. I'm not testing that directly. You'll see that I use this word decoupled here. I want to make sure that the tests are not like very brittle. And one way that they can be brittle, but also can be very correct, is if I was to change like this value here, right? This balance is known, and therefore the tax associated with that is known. So I could just put EQ here rather than not EQ and give it like, I'm gonna just guess, we'll do 98.53. How close am I? Gave too much to Uncle Sam. I can put this in here very rigidly and make sure that these tests actually pass. The problem with doing that is that if we're thinking about this abstractly, the tax may actually change in the future. Death and taxes, man. So when we actually have this value set rigidly and something outside of this function could change and cause this test to fail, we're not actually testing whether or not the logic of our function is valid. We're testing whether or not the tax is exactly the same, right? Like it becomes more brittle based upon something that's not code related. So that's why I decide to do stuff like not equals here, because it just means that what I'm actually testing, the logic here, is that the balance should be lower. All right, I like this a little bit better. So what I'm doing here as well is I'm saying the balance has to be less than whatever the starting price was. There is some magic numbery stuff here where if I change anything up here, then we're in problems. But frankly, like reading this test is simple enough that I'm not super worried about it. The main thing that we're conveying here is that this balance is expected to change and is expected to go down by at least the amount of the value of the thing that we're buying. That's useful, and it's more useful than saying the exact thing. I'm not sure if that idea of decoupling makes sense. Frankly, I'm not really certain how much I like any of the ideas in clean code, but I've seen where if you write tests too rigidly, they become very brittle. And then you're just spending all your time writing tests. You're not actually making yourself more confident with what you've actually written. More fun edge cases. So we have like no quantity. If there's nothing left, can I buy something? We should expect to see our balance remain the same and that the quantity remains the same. Things like, oh, if you don't have enough money, that your balance will still remain the same. The transaction gets declined and the inventory still remains the same. Though, actually, let's change this. I'm going to make this like 5 because I want to make sure that that's wholly separate than the case where something doesn't exist. The transaction failed because I don't have the quantity versus I have it and I can't remove it. This is very pedantic, but I think in terms of like theory of testing, this not enough money may not actually be testing that depending upon the logic of the thing that I'm testing. So yeah, let's make that bigger and I don't know. I'm willing to bet $100 that it just works. Hey, and it does. Cool. Okay, well, chapter 6. The first thing you might notice is that I have this big uint. That's because I'm using IPv6, and I can't just shove all of that into an unsigned integer, even 128 bits, because it's bigger than that. So I'm actually using this this library to make that easier for me. So the code has changed there, but it shouldn't be anything that's like that crazy. I'd also say that this shows up a lot if you're not using these strongly typed languages. Like I said with edge cases, it behooves one to pick stuff that's right about to roll over or give it stuff that's outside of what it expects. Those errors are compilation errors in Rust. I wouldn't expect anything interesting or fun other than you're not calling it with the right thing. It's not even going to compile. Why waste your time? Which is exactly why Rust is just nice. Anyway, we have our enumerables that we're actually testing here. I did try to do something a little bit more fancy here. Initially, I was trying to use like string.parse. Down here, you can see that I'm just grabbing the element from the vector, calling parse on it. And then there's this guy here. This is what they're calling the turbo fish. And I was trying to parse it into a particular type and I couldn't get it to work. I think that it's going to make more sense to me in the very near future. But you can see here they say, because parse is so general, it can cause problems with type inference. As such, parse is one of the few times we'll see the syntax affectionately known as the turbofish. This helps the inference algorithm understand specifically which type you're trying to parse into. Well, you can try that. What we did was we did string from radix, and that worked fine. So I could make this prettier. I'm not gonna make this prettier. I don't want to have to deal with like how do we make all these V's different. Maybe I'll just treat this as a lesson to the reader. If there's a way to make this nicer in terms of what it's supposed to do, but also not make it more clever. Like I think the fact that it is simple is helpful in understanding exactly what we're intending to do. I don't know. I don't like it. It's too many lines, frankly. So yeah, what we did was very similar to chapter 10, unknown previous chapter, where we just took main and kind of slapped it in and started writing tests around the examples we gave. Nothing crazy test structure-wise or usage-wise. It is worth pointing out, though, that I did run across stuff that wasn't in the book that I had to learn in order for me to continue. Writing tests is a strange thing. It falls into that weird liminal place we call wisdom. Doing these tests just means that you have more time doing Rust and actually building out that skill. If you're like me and it takes you forever to produce stuff, so you just kind of turn away from it and never actually get anything done, doing tests is a great way to go over all the things you actually did and make sure you understand them. Okay, chapter 5. I think I would make some minor note to say that when a test is simple enough or a function is simple enough, you can test multiple things inside of one function. Well, it saves you the time of having to have a bunch of different tests. I like the idea in this case, this can hold. We just do a couple, I expect some things to be able to hold here and I expect some things to not be able to hold here. Putting those all into one function doesn't really cost us anything other than having maybe slightly more granular errors. But when we're talking about the actual errors that are going to show up when we run tests, it'll be very apparent which one of these broke and what we need to do to fix it. I don't really think that we get a whole lot if we actually broke this out into assert can hold happy path, assert can hold not. Oh my goodness, I wrote a lot of comments. There's nothing exciting in this. There's nothing here that's particularly interesting, but now we get to talk about the fun one. Chapter 2, little bit of knowledge bias with Git. I'm gonna show the logs that we have. Our initial code, let's pull that up. Yeah, okay, so this main function's pretty simple. Chapter 2 simple, but it does a bunch of things that are actually kind of hard to test for. While I wouldn't recommend writing tests for something like this because it's simple enough that you should be able to kind of suss out where the problems are just by using it. But if you are in a situation where you need a test for this, we have some problems. First off, we're using random, right? So here's some RNG. That's not going to be known to us. We can't initialize anything here before our test. Secondly, we're using standard in, standard out, like it's waiting on user input. What do you do when you have to wait for user input? How do you test that? And then lastly, we have this loop here. There's not really anything we can interface with other than standard IO. And it depends on how standard IO is used. Is it locked? How could you interface with this without running a separate program? Does that make sense? Like the function here, wouldn't it be to call main and then use it? So first example was just me kind of trying some stuff out. What I'm doing here, you would call dependency injection. The long and the short of it is you want to try to determine what piece of code you're looking at, what its dependencies are, and then try to make the class function independent of those dependencies.
Oh dear God, no. They're codependent! Run!
So let me walk through how I kind of got here and then where the tests kept going as I kept figuring out how to test for this. So the first thing, I determined IO and reading and writing to it would be a problem. I want to remove them from this actual function and then pass them in so that I have control over what they look like and what they are before they get into the function. We can see here we have this standard prompt, and we also have standard out capture. So standard in prompt, I gave it the same trait as the actual standard in that we're expecting to use inside of our main function, the way it regularly performs. The thought here is that I can eventually decouple this buff read from IO and then make it something else. So if the function is expecting something like standard in, I might not want to pass it standard in. I could just give it a string that has delimiters for when I want a new line, and I want it to read that the same way that I would have standard in pass that information to it. The problem here is that I made this a function, and yes, this will work, and yes, I'll have to pass this input and output in, but no, it doesn't actually save me at all. I didn't decouple it officially yet. You'll see when I actually go down to my test here, I have my happy path where I'm like, expect to put in 10, and then I'm expecting the output to look like 10. And I don't really care whether or not the function terminates its loop or whatever. That maybe makes sense. But then all of a sudden I'm like, okay, well, what do I do after happy path? Like, how do I say I want to test that it's too low or whatever? We recognize that there's another dependency here, the RNG, but we also recognize that I didn't decouple the logic or the thing that it's doing from the function. What I did was I just moved it to a different place. So how do we decouple that? On to the next commit. This was where I started to ask a lot more questions to my friends and bother them a lot more, because it's hard to make sure I can express this theory to you guys, but also do the rest associated with that. The implementation of what dependency injection looks like in Rust is just necessarily going to be different than other languages that I was used to. So we have this output function. If I pass this function in as a parameter, I can still use this inside the function for standard out. That works as expected. However, we have another problem, right? Like the trait here needs to be satisfied for whatever the generic type that I'd put in. And while this works, we have this problem where this trait is concrete. It's again talking to like the brittleness of this code. So what makes sense is to stop and say, what is this trait? Should I make a trait that encapsulates IO right, and then whatever else I intend to use for this? And that's when we actually start having, well,
And you fail.
more problems, but we're starting to work towards the logic of testing this. I make this output to user trait. This output to user trait is actually going to be used on an object that I can pass in. So this user struct. This output to user struct then needs to be able to, one, print to standard out, but two, hold these values for testing. By doing this, I have a regular struct, this standard out struct, which is going to do exactly what it did before. But then I can make a different struct down here, which does something different. This one has an attribute called contents. And now I can, instead of doing print line when we call give user output, what I'll do is I can just push whatever the output was from the program into this vector and make sure that it's the same type as what I'm expecting. And then we're happy, right? Now our trait here is output to user. Output to user can be two things. It can be either output to user mock for testing or output to user standard out. Both of those have different implementations of that behavior. Turns out traits are good at describing that. We also will change our standard out capture from being this function to then being the actual struct. So great, so it's all done and everything should work. Not quite. I did one other thing here. I also didn't do IO yet. We're going to talk about that in a sec. But the output here, I give it strings because that was what the function was initially. The problem here is I gave a different type when I created give user output. Why did I do that? There's only so much output that this actually has that I need to be worried about. Here's the guessing game. Guess the number, too high, too low. You won, congratulations, or you failed. So that is pretty easily described in an enum. The nice thing about this is that I can make this enum exist in different locales. I can have all that business logic very clearly defined, and that way I can swap out whatever the actual values are for that enum whenever I make this different in a broader business sense. This is what most would consider overkill, but it is a useful thing to think about in terms of how we structure our programs. It makes it much more viable for us to change this in the future and to make sure our tests are like very clear, correct, and not just saying like this particular string needs to be this. Because if I change that inside of main, now I have to change it in all of my tests versus now it's an enum. It's going to be whatever it is in that enum everywhere inside of the code, and I can change that enum and have all of them change inside the code pretty easily and pretty clearly. Okay, so did I write the tests? Not yet. The rub here is that I still haven't updated my standard in. I also haven't clearly figured out all of the dependencies that we require. I was thinking there's some thinking ahead here with this user output. At this point, it probably would have been better to just keep it as a string, but hey, we're here. So standard out has been done, and standard in prompt, well, that needs to be now broken into some traits and then some structs and then passed in and then using all those like we talked about. So let's jump ahead to the most current commit. And boy, oh boy, we got some more stuff. So cool thing. We're now doing some interesting stuff with Rand. We'll talk about that in a sec. But we have our standard input now broken into traits. Broadly speaking, I'll keep hammering this in because it took me a minute for me to grasp it. We can make a particular trait. That trait will encompass the behavior of both the regular use case and the test use case. Then we can make implementations of whatever we intend to do, print it out to standard out, save it in a vector, consume it from a vector, consume it from standard in, whatever that looks like. We can make implementations on different structs and then pass those structs into wherever our function is. That is the dependency injection. So let's look at our input from user. The standard thing we're expecting here is that we have this trait and it has a function called readLine generic. Why not just readLine? Because readLine is used elsewhere and we're going to have issues unless we either alias it in our use or we just make a different name, which is probably a lot easier. So let's look at this. This trait, input from user, is going to be used in two places. One, we need to implement it for input from user mock for testing, which also has a vector. We're going to ingest from that. But I also wanted to have it read from standard IO. This is extra. This is a little bit more. So first off, why do we have lifetimes here? Elided, elided. Implicit elided lifetime not allowed here. So it was like, I don't know for standard lock how long you expect these these things to exist for self, right? Like what is the lifetime for this? If we look in the Rust documentation, we can see that standard in lock has a lifetime specifier of static. We need to now concern ourselves with the actual lifetime of standard in for everything that's, in this case, self. That means for every function that exists inside of this implementation, we need to worry about the self lifetime. So what I'm doing here is I'm specifying for all the functions inside of this implementation, all of the references in the signature have the same lifetime A, in this case, self, and standard IO, standard lock. So, God, that is a mouthful. That handles the situation because none of our functions are introducing anything or handling the lifetime of standard in IO lock itself. So when self no longer exists, that's when we can say, you're good, you're fine. This trait's no longer applicable. In the case we're testing, we have our struct, which just has the vector, and our implementation of that is just going to be to pop off one of the values. I will say that there's a problem where popping is going to be from the end of the list, so you'll see some reverses in the tests. But what this means is that we actually look at self contents pop when we do read line generic for our mocking or for our test case, and then for our real life case, all we're doing is we're just reading standard in lock and then having the same expecs that we had before in read line. What does this look like in our main function? Well, we have standard in, which is about what we would expect, and then we can pass that in and it'll pass the specific checks. The standard out was simple enough to just have the function do a print line, and so we actually generate our struct here and then pass both our input and output into our guessing game loop. Now, what about those enums we talked about earlier? Well, the enum here actually is pretty simple, same setup as before, though I gave debug and error strings because it's going to change each time. It's not going to be statically defined and in the code section of our binary. What we're doing here is I'm just saying the greeting is whatever that greeting is to string, and for our debug and error instances of user output, we're actually just passing that guess in the match to a format macro. And that way it'll just get outputted as expected when we actually call it. So toString is the thing that we're interested in on user output. If we wanted to do localization here, we could have toString localized, read something from the system or whatever, and then say, okay, here's the files that would contain, the following lines, and we would read that into our toString localized, ta-da. The actual logic here is nothing super exciting. I know that we haven't had a bunch of examples with pattern matching and I had to look it up, but what we have here isn't radically different than just having the strings being passed in. It affords us the ability in the future to change stuff and to know exactly what we're testing. This does mean that user output inside of our main loop needs to be used basically wherever we would do the print. So you'll see that I have user output greeting, user output debug, user output hi, low, goodbye. And then if we have an error, we can pass in user error. This print line is, to debug, I guess, but we don't need that anymore. So we can get rid of that. This is what the function actually looks like now. How exciting. Okay, so now RNG, other fun things. I needed to have a different library. The main RNG and RNG core that we were using above are still going to work the same. So when we go down to our main call that calls guessing game, this RNG that exists in the parameters is the same RNG that we'd get if we just initialized it right above our RNG gen range. It's just now pulled it out, and that's nice. So how are we going to use this for testing? Well, in our testing module, we're using a different kind of RNG, a really bad RNG. In fact, not really RNG at all. As you might be able to intuit by this point, the pseudo RNG-ness of this is very nice because we can set the value we expect RNG to return by making sure that it's not actually random. And then we can ensure that the output is exactly what we expect. The reason I'm using seedable RNG for some of this is because the way that we actually call gen range here isn't patched. I shouldn't say patched, is not defined for step RNG, though it does change the pseudo randomness that it would use to generate a value. So we know that whenever gen range would be called, the RNG that it would use will return a 1. And in our first test, we're actually just saying, hey, I expect when I give the output 1, it's going to give me a goodbye message. And so we'll see the same enums we're seeing before, and that works perfectly fine, knowing that the happy path is real simple. But we have a problem where we want to say, hey, I want to guess too low, where we want the number to be generated very high, and then we can guess a bunch of low values. We can't test that if it's only ever going to return 1. I just kept step RNG for what we had now, and then I ended up using seedable RNG later. But let's make sure this all makes sense from the testing perspective. For review, now we have decoupled our standard input, standard output, and RNG. The standard in and standard out, we now define traits, implement different behaviors for that trait to either do exactly what we were doing before in main, or to change what we were doing and make it more easily testable. So in this particular test, standard in is using our input mocker from testing, right? Our implementation that's going to have a contents attribute. The contents attribute is now just a vector, which has the following 1 and a new line in it. Then we can do the same for standard out, output to user mock for testing. This one's an empty vector, which it will populate when it gets called. We make our RNG, which is terrible RNG, but works great for testing, where it's going to expect to return 1. Lastly, we make sure that we understand exactly what we expect to get out. So what I'm going to test on is the output, the thing that it would be reporting to us. And I'm expecting that it's going to give us a greeting. It's going to output a debug message of 1, what we guessed, and that output 1 is going to be equal to what we have in our RNG gen range. That's going to pass, everything's happy, it says goodbye, and then exits the loop, and then we can then call that and assert they're equal. What a tangent, right? Like, what a wild set of things to test for something that shows up in chapter 2. But we're not quite done yet. I'll just go through the rest of them just to give you more examples. Our 2 low examples. So this is where we needed to make the RNG higher, and this is where I can call seed from U64, and that seed is allowing us to change what value we're getting here. This is a magic number. It's just when this seed is here, we get a value of 89. I just picked 182 and it happened to be high enough for me to be able to do this test, but you could just change that value each time until you get what you want. And in this case, now we have our contents, and I actually call a reverse because, as stated before, this pop that we're using in our read line generic, it's going to read from the end of the vector. And when I don't reverse it, this vector here is going to actually be 89, 20, 10, and 1, which is not what we want. The output for this expected here is maybe a little bit different structurally, but it should make sense with what we're testing. We expect the greeting, we then test 1, it tells us it's too low. We test 10, it tells us it's too low. We test 20, it tells us it's too low. We test 89, it says you're on the money, goodbye, whatever that goodbye message is. Too high, in the same vein, it should do the exact same stuff. I just didn't reverse the output. It's going to guess 99, 48, 23, and 1, and we see the same output in the expected. Should work as expected. We also can test stuff like, what if I don't give it the right thing? And this is where we're actually going to be using that error. In this case, the standard in, I give it a contents of a non-parsable into an int value of a string, and I'm expecting that it explodes. What I do is I have just should panic, and the expected value is please type a number. This please type a number is just a string inside of our function, but what we can do here is we can change this to user output. This ugly mess here. So what exactly are we doing here with all these 2 strings and stuff? First off, we change the string to a user output error, and what the user output error needs is a string, like capital S string. So we give it a reference string, and then we call toString on it. So now this user error exists. If I was to end this here, it'll be mad because expect is expecting a string reference. Well, we wrote a function for user output called toString. This function returns a capital string, but we can call it to get the output we're expecting, where we're actually taking that error and passing it in. But then what we see is that it's upset because, well, it's expecting a string reference or string slice, and we're giving it a capital string. So that's the last guy we add here as str. I think that this is more complicated simply because toString exists in the standard library, or sorry, exists on the string type, and then toString also exists for our user output type. What I probably should do is change the toString to a different function name so it's more clearly discernible where it exists, and then this as string here probably isn't necessary if I just have it return a string slice. I don't necessarily like that though, because when you have a struct, like we maybe talked about before, returning a string slice isn't particularly useful when we have things where we need to pass it in and would then need to exist in the heap either way. So I don't know. I don't have a great way to answer this other than this looks gross, and yes, I know. There's one more thing that I'd like to talk about, though I'm not certain how exciting it will be to talk about. CI/CDs, I mentioned that at the very beginning. What is that? Well, for my particular Git repository, I can define a Docker image and then tell it to do some stuff once that is up and the code is there. Basically gives you a little environment where you can make sure something happens when you do something to your code. CI/CD, continuous integration, continuous development. What is deployed to production, you're continuously deploying, and then your integration, how everything gets built as you push code. What this means is that when code gets pushed up, it will trigger a pipeline. I have CI/CD configuration, which will bring up this guy. But what this does is it will start some stuff to be performed whenever the commit actually starts. So this test here is going to pull that image down and then run the tests. So you'll see it pulls it down and then runs the test. And this way we can confirm that certain things have to happen in order for code to get merged in to our main branch or protected branches. In this case, we passed, and so everything's happy and we get our little green check marks. It's another way to ensure that people are actually writing the tests that we expect them to. The state of the code is also what we expect it to be. We can go into more of that into the future. I think largely there's enough resources out there, except for resources associated with the GitLab webhooks and Discord. There's like no information about that. The only way I was able to have this work back in like May was when I self-hosted the runners, because inside the runners you could actually just put whatever environment you need there, and I can't commit that into this file because the webhook doesn't work. So this isn't going to work until I have more time, or I'd rather just write Rust code. Like there are like 5 meta things in, and it's just not worth it at this point. All that to say, when we finally run our tests and they work, the satisfaction. There obviously was a bunch of stuff that I had to do and learn and write up for this episode to make sense. And as a one-person army, it sometimes takes a little bit of time. I am really excited about the next chapter where we're actually getting to write IO stuff. And for that reason, I'd like to just, offer a little bit of an apology. It's taken some time. Hopefully the quality's a little bit better each video. And, we're more than halfway there, so...
Catch your breath, man. Shake out those lips. It's downhill from here.
It is downhill from here.